Hi everyone, welcome to Janani Trust Bangalore. To get a good information related to competitive examination, don't forget to subscribe this channel. To get continuous information, please press the bell icon. Encourage us through your likes and comments. This is the third part of the wave chapter of the physics course. Make sure you have watched already two videos we have covered under this chapter. Still you have not yet watched those two videos. You can find those two videos in a playlist. Go to that, go through it. In a first part of this chapter, we have covered waves introduction, and the second part of this chapter, we have covered types of waves. In this session, we are going to discuss about the formation of waves and waves terminology. And again, I have added 3 to 4 MCQs in the last session of this video. Please try to answer those MCQs, very much important to your examination point of view, so that I can understand how much you are understanding. So please try to cover all the 3 videos and at last come to the question answers part and give your answers in a comment box, so that I will give the correct answers to your tried answers. Okay. Please try to answer those, cross check your capability there. So let's see the formation of the waves. So we have come across already mechanical waves and mechanical waves subclassification. There you can find two waves, longitudinal and transverse waves. The particle movement also we have seen. Let's see the how the wave formation in transverse wave and longitudinal wave. Let's label the transverse wave while transporting energy from one place to other place. Okay, I have taken the slinky example in the last videos. The slinky, when you apply energy in upward direction, it looks like this. The slinky has given the movement like this. That means it will follow the certain pattern. The transfer wave is following this pattern to transfer the energy from its source to end point. Okay, while creating the crest and troughs. So this is the crest and this is the troughs. So in the transverse wave, the energy is transporting, and while following this pattern, this is the pattern of the transverse wave. While following the pattern, the wave is creating crests and troughs. Okay, the particle is moving upward and downward direction. So while it is moving upward, it is creating crest. While moving downward, it is creating troughs, and it is continuous, and the waveform is also continuous. Okay, this is the transverse wave, how it looks like. Next, come to the longitudinal wave. So the longitudinal wave, I have to consider certain particles. Okay, so I am taking certain particles. So consider these were the particles. If I applied initially energy, so that energy is transported from initial position to end position. So how it will transport in no sense? By creating the compressions and expansions. So you can see in this region, you can see here, this is the compression region and this is the expansion region, and again it is compression region, again you can see expansion region. So that means in a longitudinal wave, the disturbance is traveling in a straight line. Again the particle movement is also in the same line. It will start to oscillate about their mean positions in this way. Particle movement is moving in this format. But when you apply initially, the particle start to compress a lot. So that means it will create the compressions here. So compressions in a sense what? The particles are in this region, the particles are compressed a lot. So the distance between particle to particle are very less. It is the compressed region, very much compressed. And again welcome to the expansion. Also it call it as the rarefactions. Okay, in this rarefaction region, the distance between particle to particle is more when compared to the compressions. Okay, so in a longitudinal wave, the disturbance is traveling from one place to other place while making compressions and rarefactions. Rarefactions also called as expansions, and compressions and rarefactions again called it's also called as nodes and anti-nodes. So this is how we can label the transverse wave and longitudinal wave. So this is how longitudinal wave and this is how transverse wave. The transverse wave looks like this in a medium and the longitudinal wave looks like this in a medium. Now let's see the graphical representation of the longitudinal wave and as well the transverse wave. So for graphical representation of the transverse wave and longitudinal wave will be same. Both might be same. For a graphical representation, what we need? Two axes. So this is the y-axis and this is let's take this horizontal line as x-axis, and y-axis representing a displacement and x-axis is representing a distance. Okay, I am writing it as a distance. So this d representing a displacement. Okay, so here this is the particle movement, how we have the wave looks like in a transverse wave. So let's consider one particle in a transverse wave. This is the main position. This is the particle where I have placed. So the particle I have written in a bigger size so that it will be clear to you. So when it has no energy, it is rest in its main position, while if I am giving a little energy, it displaces to this position. That means it's covering certain distance. It's going to a maximum distance. Again it coming back to this position and again it will reach to this position downward. Okay. So that means it completing the one oscillation. So the particle is moving this place and again it is displacing and it is coming to this place in the transverse wave, upward and downward direction. So if you consider the particle in a longitudinal wave, so in a horizontal and the particle is here, it will displaces up to this way and this position, again it will displaces to this position. So there is also a particle displacement to maximum this place and this place. This is the transverse wave displacement. This is the longitudinal wave particle displacement. So the particle when it is moving to here, there is a energy. Okay, it moves here. Again it is coming back to this main position. What it means? Why it is coming back to main position? What is there? Who is bringing back this particle to its main position? So there are again some intermoleculars. Here you can see there are other molecules, other particles also. Between those particles, so you can say there is an intermolecular force always present. So when this particle displaces to this position, all that molecules are try to bring this particle to its original position. So that means you can call it as this particle has a restoring force. Also you can call elastic force. Due to that restoring elastic force, the particle has a tendency to come back to its original position. Okay, the particle is reached to main position. Again, what happened? Again it is going to the downward direction. What happened? Why it is displacing to here? Because the particle, while it is traveling to this position, it has velocity. That means it has kinetic energy. Again, the particle has certain mass. Due to that mass and velocity, mass in a sense inertia. Due to inertia and velocity, the particle reached to this position. Again, it will go back to this position because of elastic force or restoring force of this particle. So this is how the particle is moving. The particle is able to create oscillations about their main positions. While it is moving to this position, the particle is reached this position, and while it is coming back to main position, it will come here, and while it is coming back to this position, it will reach here, and then again it will go back to here. It will finish as one cycle. So that is one oscillation of that particle, one vibration of that particle, you can call it as a one cycle of the particle. Understood? So the displacement and distance graph and the longitudinal wave also, it same, it looks like same. So here now this is how the graphical representation of the transverse wave, and as well I will write this is also for longitudinal waves also. For both it is same. Now let's see the terminology of the waves. What is the terminology of the waves? Why we need to understand the terminology of the waves? Okay, the terminology is very much important because I have taken only one particle here. If you consider many particles, the many particles will make many oscillations. Those many oscillations follow pattern. So again this is the pattern and it will make a many waves like this. So one wave to other wave, if you have to find out the difference, if we have to make the difference from one wave to other wave, we need to know the terms of the waves. Some of the important components of the wave we need to understand so that we can make it a differentiate between one wave to other wave. It is helpful to differentiate distinguish the waves. Understood? So here let's see some of the important components. First component is amplitude, next is frequency, and next is time period, and next is wave velocity, and the next is wave height, and next is wavelength. So these were the important terms which we are going to discuss. Okay, first come to the amplitude. What is amplitude? The particle, I said, about a mean positions, about a certain it is displacing to a position, right? So the particle is displaced to a maximum distance. So it is covered the maximum displacement from its mean position. See, the particle is going this. At last it reached this position. So that is the maximum displacement covered by particle about its mean position. This is the maximum displacement. This is the maximum displacement of the particle. That is only amplitude. Here also you can represent this is the maximum amplitude of this in a lowest way. So in the lowest, in the trough, in trough side also, in a crest side also you can get a amplitude. Maximum displacement of a particle from its mean position, either from its directions of mean positions. Okay, so this is the amplitude. Amplitude, it is denoted by the small letter x or small letter a. Okay, and its a SI unit is in meters because displacement, right? Its a SI unit is in meters. Now let's come to the frequency. What is frequency? So here to tell the frequency, the particle is covering number of oscillations. We knew it, right? So if you defined the time, you are considering 1 second, that is defined time. I am taking defined time, that is 1 second. Within 1 second, how many oscillations can particle can able to complete? So that number of oscillations is called as the frequency of that particle. So within a time limit, so within 1 second, the how many oscillations can be completed by particle are called as frequency of that particle. If any particle, take this is only a particle, this particle is making 60 oscillations for every second. So that means the frequency of this particle is 60 Hertz. Okay, so it is denoted by the small letter f and its SI unit is Hertz. So how it is denoted and how it is denoted, and again the SI unit of all these terms are very much important. Okay, next come to the time period. So on this time period, to complete one vibration of the particle, it will take certain time, right? Certain time is necessary. It is completing one oscillation, it takes 0.01 second, maybe a 0.02 second, certain time it will take. So to complete a one cycle of the particle, how much time it period. Okay, the time period is denoted by the capital letter T, and again its SI unit is seconds. To finish the one cycle, how much time it is taking? The time is only time period, and the graphical representation for the time period, x-axis would become a time. So I will write here it as the time. Okay, so when it is a time, x-axis represents the time. Forget about this distance. Displacement and time graph would give the time period. Understood? Only for time period you have to represent x-axis as the time. So I am writing there itself. Just consider. So when you are considering a time period, just forget about the distance. Time and displacement you have to consider to finish the one complete cycle. So this you can call it as the one complete cycle. So one complete cycle, it takes a time. That's the time is only time period. And next come to the wave velocity. So what is wave velocity here? To complete a one complete cycle, it will cover the certain distance. Again, the distance, and within a 1 second, how much distance it is covered. So within 1 second, how much distance the wave is covered. So that gives the wave velocity. Within a defined time, how much distance the wave is traveled, that gives the wave velocity. Again you can say it as a distance by time is what? Speed, right? But in a waves I am taking it as a wave velocity because the wave is traveling in a particular direction. When it is following some particular direction, we have to make it as a vector quantity because direction is there, and again it has a magnitude. So due to that I am representing it as a vector quantity. Velocity is a vector quantity, speed is not vector quantity. Okay, that is scalar quantity. So you have to represent here wave velocity equals distance by time. So that is distance as how much distance it is covered wave within a defined time, that is 1 second, which gives the wave velocity. It is denoted by the capital letter V, and its SI unit is meters per second. Okay, next come to the wave height. So here I said the amplitude. Here in the waveform, this is the maximum distance in this direction. This is the maximum distance in this direction. So the distance between the crest and the trough, the distance between the crest and the trough is called the wave height. The distance between the wave crest and to the wave troughs gives the wave height. And the next come to the wavelength. What is the wavelength? To finish the one complete cycle, it has to follow the certain distance. So it means it has to cover certain distance to finish one complete cycle. Okay, so that distance is called as a wavelength. So this is one complete cycle. To finish that complete cycle, it has to cover certain distance. The distance only wavelength. The wave is covered certain distance during its cycle is called a wavelength of that wave, wavelength of that particle. It is denoted by the Greek letter lambda, and its SI unit is again meters. Its SI unit is again meters. So this is the wavelength, and wavelength again. So not only you can consider the distance between the cycle. So you can also make any, see, this is the distance. If you consider this is the successive point, and you can consider the next successive point of this point is this. Okay, this is the successive one cycle, and again next successive cycle is this one, right? If you consider any point in this cycle, and that consecutive point of that point gives the distance between two consecutive points will gives the wavelength. So if I am considering this is the point, what is the consecutive point of this point? This is the consecutive point. The distance between these two also gives the wavelength, and you can consider here to here, any points you can consider, the distance will be same. Okay, and also wavelength can also called it as the distance between the two consecutive troughs or two consecutive crests. In a longitudinal wave, two consecutive compressions or two consecutive expansions, which gives the wavelength. Okay, minimum distance between the two successive points of a waves. Okay, this is about the waves terminology. I think most important points I have covered under the waves terminology. Now let's see the relation between the some of the waves terms. Okay, how the time period and frequency related to each other. So I said the frequency, number of oscillations, time period in a sense to complete one oscillation, how much time it has taken. So let's see, if the number of oscillations more, how the time period is lesser. When the time is taking, the particle is taking a less time to complete one oscillation, that means within a certain time it will give the maximum oscillations. Time period is less, it will give the maximum frequency. That means time period and frequency are indirectly proportional. So when time period is less, frequency is more. When time period is high, the frequency is less. Number of oscillations were lesser. This is how the frequency and time period were related. So the frequency is indirectly proportional to time period, 1 by T. This is how you can represent. And again, frequency and wavelength, how both were related. So when the frequency is more, number of oscillations is more, I said that time period is lesser. So when you are considering relating to the wavelength, that is the distance between one successive point to other point, right? So the distance is maximum. At the time, the wavelength is maximum. When wavelength is more, number of oscillations will be less. Again, the wavelength and frequency is indirectly proportional. When wavelength is more, frequency is less. When wavelength is less, frequency is more. So, how these two are related to a wave velocity, that is V. The wave velocity is the product of wavelength and frequency. So, lambda cross F, which gives the wave velocity. Both were indirectly proportional. If you need to find out the lambda, you need to find out the lambda, wave velocity by F. You need to find out the frequency, what? Wave velocity by lambda. So the wave velocity, how it is related to wavelength and frequency, which it is the product of the wavelength and frequency. Wavelength and frequency. This is how all these terms are correlated. Is very much important. And this frequency and time period, wavelength and frequency, and again wave velocity, all are very much important. So let me take one example. If a particle is moving in a, so consider the particle A. This particle A is moving in 600 meters per second. That means wave velocity is 600 meters per second. Again, it is making 30 oscillations. So that means its frequency is 30 hertz. 30 hertz. The particle is moving in 600 meters per second. Wave velocity is 600 meters per second and its frequency is 30 hertz. We need to find out the lambda, wavelength of that particle. Let's see what is the wavelength of that particle. What is the formula for that wavelength? We know wave velocity divided by frequency. What is wave velocity? 600 meters per second. And what is the frequency? 30 oscillations. So you have 20 meters. So what is the wavelength? 20 meters. When it is the wavelength is more, the number of oscillations were less. See, wavelength is maximum, 30 oscillations were very less. If you are substituting 300 oscillations, you can get a, if the frequency is 300, let me take one more zero here, 300 oscillations. I will substitute just 600 meters per second wave velocity and oscillations. Frequency is 300 hertz. Just see, so you can get 2 meters. See, what is a wavelength? 2 meters. So that's how lambda and the frequency always inversely proportional. Inversely proportional. One is maximum, another one gives less. If it is maximum, it is less. This is how both were correlated. So this is about the wave terminology. I hope you understood all these definitions thoroughly. Let's see the official definitions of the terms. First is wavelength. It is the distance travelled by the wave during its one cycle. It is denoted by lambda and its SI unit is meters. Amplitude, the maximum displacement of a particle of the medium on either side of its mean position. It is denoted by X or A and its SI unit is meter. And time period, the time taken by the particle of the medium to complete its one vibration is called time period. It is denoted by T and its SI unit is seconds. And again frequency, the number of vibrations made by the particle in 1 second, that is defined time. Okay, it is denoted by the small letter F and its SI unit is hertz. And wave velocity, the distance travelled by the wave in 1 second. Again it is defined time. So that is wave velocity. It is denoted by the capital letter V and its SI unit is meter per second. So these were the official terms, official definitions. If you need, pause the video and write down. Okay.